So you've got all this data, right? Piles of it. But how do you actually use it? How do we go from just staring at spreadsheets to making smart, confident decisions?
That really is the million-dollar question, isn't it? And thankfully, there's a whole scientific framework designed to answer exactly that. So today, we're going to break it all down.
Okay, so where do we even begin? Let's say we have an idea we want to test. Like trying to figure out if a new ad is actually better than the old one.
Right, and this is where we have to get a little formal. It all starts by turning that business question into a testable, statistical statement. And we do that using a process called statistical hypothesis testing.
All right, you're throwing around this word hypothesis. What does that actually mean in this context?
So we start with something called the null hypothesis. Now think of this as the default assumption, the status quo. It's the skeptical, prove it to me position. It's basically saying, hey, there's no difference here. This coin is fair. Or these two ads, they perform exactly the same. This is the baseline that we're going to try to knock down.
Okay, so it's like we're setting up a showdown between two ideas. You've got the null hypothesis, saying nothing to see here, no change, and then the alternative hypothesis, which is the cool new effect we're actually hoping is true.
That's it, exactly. And our whole goal, the entire point of the experiment, is to gather enough evidence to see if we can confidently say, nope, that default assumption is wrong. And here's a key point. We're not trying to prove our new idea is right. We're trying to disprove that the old way is the same. It sounds like a small difference, but it's absolutely crucial.
Okay, so how do we measure this evidence? Is there like a single number that just tells us, yep, your result is a big deal?
You bet there is. It's called a p-value, and you can think of it as a surpriseometer. Here's how it works. First, we have to assume the null hypothesis is true. So for a minute, let's just pretend our coin is perfectly fair. Then we do our experiment. We flip it 1,000 times. And now we look at our result and ask, okay, if this coin really were fair, what are the odds we'd see a result this lopsided just because of random luck?
Got it. So a tiny p-value means our result would be a huge surprise, a really unlikely fluke, if the null hypothesis was actually true.
Precisely. In our coin flip example, the p-value turns out to be 0.062. So what does that mean? It means there's a 6.2% chance of seeing a result this lopsided, or even more so, just by random chance, with a totally fair coin. Kinda surprising, but not crazy surprising, right?
And the idea is, if that number gets small enough, and the common cutoff is 0.05, that's when we get to say, you know what? I'm rejecting the idea that this coin was fair in the first place.
Okay, that's the theory. It makes sense with coins, but let's see how this whole framework applies to something we see all the time in the real world, a classic A/B test.
So for this, our null hypothesis, our default assumption, would be that there's no difference, that both ads get the exact same click-through rate, right? That's the one. Our null hypothesis is that any difference we see is just a fluke. Now let's look at the data we collected. Ad A is sitting at a 20% click-through rate, and ad B is at 18%. So the big question is that 2% gap a real difference in performance, or is it just random statistical noise?
Okay, whoa, new number on the screen, -1.14. What is that, and how does it get us closer to an answer?
That's called our test statistic, in this case, a z-score. We basically plug our data, the views and the clicks, into a formula, and it spits out this number. It tells us how far away our result is from the no difference scenario, measured in standard deviations. So -1.14 means we're a little over 1 standard deviation away from 0. And this number is what lets us find our p-value.
Okay, so what does that give us for a p-value?
Well, that test statistic corresponds to a p-value of 0.254. Now, the common cutoff for significance is 0.05. Our number is way bigger than that, so we cannot reject the null hypothesis. There's a whopping 25.4% chance that a difference this big could happen purely by random luck. The takeaway? We don't have enough evidence to confidently say that ad A is actually better.
The process seems pretty logical, pretty straightforward, but I'm guessing there are ways people can mess this up, right? What are the common mistakes?
Oh, for sure. And the biggest, most tempting one is something called p-hacking. And this quote on the screen really gets to the heart of how you avoid it. The golden rule is decide what you're testing and how you'll test it before you ever peek at the data.
So, p-hacking, is that basically like torturing the data until it tells you what you want to hear, even if it's not true?
That is the perfect analogy. You're just running tests over and over again until, by sheer chance, one of them gives you a significant result. And avoiding that is absolutely critical. It's the difference between making a real discovery and just chasing ghosts in the data. If you want to make truly data-driven decisions, you have to avoid this.
So when you boil it all down, this whole framework isn't just for ads and coin flips. It's really a way of thinking. It's about being disciplined and honest with yourself about what the evidence is actually saying. Which brings us to a final thought for you to chew on.